those values on the number line. And I need to add S3 back in. It is 5 over 6. So S minus S1, so back to the values. So S1 is the first partial sum, it's up here. S2 is all the way back down here. They kind of bounce back and forth. Then S3 is back up here close to S1. S4 is back down here slightly larger than S2. And then in the middle of all of it is sum, the sum S, which is the limit of all the partial sums. So an interesting observation can be made here. The distance between the limit of the partial sums and the first partial sum is smaller than the difference between the limit S and S2 minus S1. We know the value of S2 and we know the value of S1. S2 is 1/2. S1 is 1. This is negative 1/2. If I take the absolute value, we get 1/2. And here's the interesting realization about that. That is A2. If we exclude the alternating part of the series, the negative 1 that's in the front, that is the 1 over k part. It is A sub 2. Now let's take a look at what happens between S and S2. Again, I'll erase the red. The difference between S and S2, which is from here to wrong direction, S2 is behind it, S to S2, that is smaller than the difference between S3 and S2, which is from here to here. S3 minus S2, oops, I erased a 1 here. S3 is 5 over 6. S2 is 1/2. 5 over 6 minus 3 over 6 is 2 over 6, which is 1/3, which is, look at that, A3, it's 1 over 3. And let's do it one more round. I started writing it in. S minus S3, let me go back and erase this. S minus S3 is smaller than, using the pattern we've, oops, I did it again. It's less than, using the pattern, it will be less than S4 minus S3. S4's value is 7 over 12 minus S3, which is 5 over 6. Finding a common denominator, this will be 7 over 12 minus 10 over 12, which is negative 3 over 12, which is, again, shocking, 1 over 4, which is A4. So now we have this nice generalization. S minus Sn is less than Sn plus 1 minus Sn, which will actually always be equal to the absolute value of plus or minus A sub n plus 1. And again, I know it's n plus 1 because if you look at your value here, it's A2 and S1. So this essentially gives us a bound. S minus Sn, so the difference between the nth partial sum of an alternating series and the sum of the alternating series is always between an plus 1 and negative an plus 1. Oh, sorry. The absolute value bar shouldn't be there. This is true. S minus S sub n is less than A sub n plus 1. The algebra behind that is then we could get rid of the absolute value bars, and it's negative A sub n plus 1 is smaller than S minus S sub n is less than A sub n plus 1. Which means the sum of your series is bounded below by the nth partial sum minus a sub n plus 1, and bounded above by the nth partial sum plus a sub n plus 1. This leads us to the following theorem. If an alternating series, negative 1 to the k times a sub k, converges to a sum s, then the error in approximating the sum s with the nth partial sum s sub n is less than a sub n plus 1. That is s minus s sub n, the difference between them, absolute valued, is less than a sub n plus 1. Next page is an example. Find a partial sum s sub n that approximates s for the series k equaling 1 to infinity of negative 1 to the k plus 1 times 1 over k, such that s minus s sub n is less than 0.005. To clarify, we just learned in the previous theorem that s minus s sub n is always less than a sub n plus 1. So our a sub n plus 1 is 0.005. That's this right here. So 0.005, oops, didn't work again, 0.005 is a sub n plus 1. Now, what is your a sub n? That is 1 over k. So we're setting 1 over k plus 1 because it's the k plus first term. Think about that for a second. It's the k plus first term because it's n plus 1. So instead of just using 1 over k, I'm using 1 over k plus 1 is equal to 0.005, and we're just going to solve this for the value of k, or the value of n. We could have used n alternatively. So this means that k plus 1 equals 1 over 0.005. I did this from remembering some stuff about how ratios work. So I flipped this upside down and I flipped this upside down. So k plus 1 will equal 1 over 0.005 is 1 over